have something to do with, well, the area of a surface of a sphere is 4 pi r squared. The key thing there is the r squared. So this gravitational force is inversely proportional to however far you are away squared. Now it also depends upon these gravitons. The greater the mass, the more that are given off. So it does depend upon the mass. It actually depends upon the masses to get the actual force. But in physics, we have this idea that they should exert the same amount of force on each other, just opposite directions, so it shouldn't matter which order I put them in. What I'm heading towards is a rationalization for whatever I'm doing with the masses, the commutative property holds. The order should not matter. Well, we got two basic operations where the order doesn't matter. What are the two math operations where the order doesn't really matter?
Addition and multiplication.
Those are the two. And so we're doing multiplication here. Now I've left this gap out front for one more thing. It now comes down to the units. So the number in front depends upon the unit system you're working in. It is known as the gravitational constant. Some textbooks will call it the universal gravitational constant, but we really don't know if it is indeed universal. It seems to be working around here pretty well, but in another galaxy, is it the same number? We don't know. We do know that things are not behaving the way we would expect them to in terms of how fast they're moving. So there are some, that's still a place of study. They also have come up with other ideas besides the gravitational constant not being universally constant. This idea of dark matter and dark energy. I've seen the evidence for dark matter. I thought it was rather compelling. Dark energy, I don't know, at some point it's just theorists throwing spaghetti at the wall. If it eventually sticks and they find actual evidence for it, then they're hailed as geniuses. Otherwise, their work just goes up in the dustbin of history and it's a curiosity. But the most important thing for them is that they published and they maintained their professorship at whatever university. That was probably more cynical than it needed to be, but there it is. So anyway, this is the generalized formula. We have been using mg specifically for weight. So this should be equal to mg, where this is the mass of the small object. But if I'm talking about Earth, Moon, I don't know what g is. I don't know what the acceleration due to gravity of the moon is because of the Earth. It's not 9.8, I know that. That's if I'm near the surface of the Earth. So when you're dealing with, say, the Earth-Moon system or the Earth-Sun system, and wanting to look at forces, this is what we're looking at right here. Now, we could calculate what this little g is, but usually don't. And on that note, have a wonderful fall break. Don't meet on Tuesday. And the two of you are going to follow me back, at least two of you will follow me back for the test.